Hello everyone. Now we are going to discuss about the topic nanoscale building blocks for optical communication, which is based on silicon. In this presentation, we are going to discuss about intro of the product, design of the device, and the operation and the experiment that has already been done. Coming to the intro of the device, as we all know that nowadays the uses of computer softwares has been developing, and also the development in optical communication is also increasing. For this, we need speed processors for smooth operations. The effort of these two needs gave birth to the optoelectronic nano devices. Before talking about optoelectronic nano devices, first of all, what is nano device? A nano device is a device that comprises one or more nanoscale components which is essential for operation. What is optoelectronic devices? The device which operates on both light and electrical currents. For instance, laser diodes, light emitting diodes, and solar devices. And the devices that can electronically control the propagation of light comes under these optoelectronic devices. And this device convert photons to electrons, and it operates on high speed, and the power consumption in this device is also less, and it reduces crosstalk and noises. What is crosstalk? Crosstalk is a disturbance caused by the electrical and magnetic fields during the process. And now we are talking about the device named silicon on insulator photoactivated modulator. As this is the basic structure of the device, and this device is controlled by light. As well as in this device, the commands are controlled through external illumination, not electronically. And used for two main applications. One is electrophotonic processing chip, where the photonic command controls is used in optical processing modules. Second application as photodetector, where the photonic information signals are detected and multiplied by other electronic signals that are passing through the modulator. Coming to the operation, the device operation held on two states. One is on state and off state, and this is the basic structure of the device. And you can see that two positive potential VCs are connected at the bottom of the channel, and that can control the clearing of photogenerated electrons, as well as the drain is connected at the top of the n-type channel, and source is connected at the bottom of the n-type region. Whereas the generation output on this device is determined by the illumination power, that means the projection of light. And you can see the red color rectangle shaped thing, which is called oxide trench, that protects the n-type region, and the gray color thing on both sides of the channel, whereas in p-type region or else in n-type region are called depletion layers. Okay, let's come to the operation. When we apply the negative gate potential at the both type of gate potential at the both sides of the p-type region, the negatively charged depletion layer forms on the both sides, as well as the positively charged depletion layer forms on the both sides of the n-type channel also. In this device, the depletion layer of n-type is designed to be larger than p-type, which means that depletion layer of the n-type region is narrower than the p-type region, and which is more than thin enough to keep the channel in open state even though the channel is in dark condition. What happens when the channel is in dark condition even though it's open? The electrons from the p-type drifted away by the negative gate voltage towards to the n-type, which means that towards to the oxide ranges, and it forms the inversion layer near to the oxide borders. The problem is this negative layer increases the inner depletion layer in the n-type region and closes the channel finally. And the only thing that we can solve this problem is by applying the positive potential to the clearing contacts which are connected at the bottom of the channel, which can clear the photo-generated electrons, which means that the inversion layer will disappear. And the combination of both this clearing potential and the gate voltage keep the channel in open condition. This is the process of on state, and we are heading to the off state operation. In this off state condition, um, by increasing the illumination power on both sides of the p-type region, increases the concentration of free generated photoelectrons also until it reaches the inversion state, as well as the n-type channel depletion layer on both sides extends widely and eventually closes the channel. And some electrons are photo-generated and some electrons drift away to the positive potentials. If the photo-generated electrons is much higher than the uh, positively potential clearing rate, it remains the p-type region in inversion state. For this, a dynamic layer has to be maintained at the surface of the insulator periphery by continuous illumination, which brings the channel to the closed state. And coming to the experiment of the device, here the evaluation of the results of the SOPM device on a MOS p-type silicon wafer capacitor. Using the capacitance voltage measurement, we can study the behavior of SOPM in two states. One is deep depletion and another is inversion, which means on state and off state under photonic excitation. Here you can see the gate voltage, and the MOS device is attached to the capacitors with the gate voltage and sinusoidal signal. When the laser light focus on the silicon wafer capacitor with a gate voltage, the capacitor is a p-type silicon substrate with an accepted density and oxide thickness. And the gate voltage also consists of a staircase step-in time DC bias with a sinusoidal signal. Here, by switching the gate voltage in the previous diagram under dark condition from negative to positive, the MOS capacitance is also changes from accumulation to inversion state. As the light turns on, here the two phenomena are observed. As the light turns on, two phenomena are observed. One is increment in the concentration of free carriers, and the second one is inversion layer partially follows the AC sinusoidal signal due to the generation of minority carriers. As the intensity of light increases, both phenomena also increases. Understand? In order to close the on state of the device, the positive gate voltage has to apply without light, which means that under dark condition we have to apply the gate voltage, positive gate voltage. The MOS move from deep depletion state to inversion state with a slow increase of capacitance with time as inversion layer is built by the thermal generation of minority carriers. As we can see the uh, pulse in this diagram, a short pulse leads to the steep change to mask appearance from a deep depletion layer to inversion state. And the behavior of SOPM has measured in another models using the Cosmal multifix simulation process. And this test is for longer structures, and the silicon layer thickness used in this experiment is 220 nanometers, as well as doping concentration. In this, the difference between the closed and open state is more than one order of magnitude in free electron concentration. Whereas in this simulation, the illumination was assumed to be sufficiently high to close the channel. Therefore, the sufficient for the generation of inversion layer at the vicinity of the channel. Coming to the conclusion, in the previous slides we discussed about the concept and the design of the SOPM device, and it is designed to operate at high modulation rate, because we already have the processors that are operates in normal speed, and we need speed processor for smooth operations and without any like hangings like that. And this device can also be used as a modulator in an electrophotonic chip, as we discussed there, and also as an advanced photo detector. And the topic is chosen from these references. If you have any doubts, please go through these differences. Thank you for your patience.